Section 15.7 is the last of the big four theorems for the semester. And this is the divergence theorem. Here's the statement. Let Q be a solid in R3, and let S be its boundary surface oriented outwards. And I put outwards in ironic quotes. I'll have to come back and explain what I mean by that. If the vector field if F is a vector field, then the double integral over S of F dot vector ds is the same as the triple integral over Q of the divergence of F with respect to volume. So remember, we've interpreted this as being the flux of the vector field F through the surface S. And I'll remind you that this quantity here is also written as div F. So since F is a vector field, we have to be dotting it with vector ds for the left side to make sense. On the right side, remember that if you take the divergence of a vector field, you get a function, not a vector field. And we're going to integrate that function with respect to V. So to come back to what I mean by oriented outwards, there's some examples where it's easy to see what I mean. If I had a solid like this, then at every point on the solid, or every point on the surface of that solid, I have two unit normal vectors. One of these normal vectors is going to point out into the air, and the other one is going to point into the interior of the solid. It's like if the solid were my shoulder, then I'd have one vector field that was pointing outward into the air, and the other one you'd have to stab into me. I don't want the one that you have to stab into me. We're going to orient the surface outward so that at every point it points out into the air. Now, for a second example, let's say that I had kind of a bead shape like this, where I've taken a solid cylinder and I'm drilling a hole down through the middle of it. Then let's think about how we're going to have to orient the different surfaces. Over here on the outer wall of the outer cylinder, I have to be oriented outwards like that. On the top, to point upwards into the air, I have to be oriented upwards. On this bottom surface, I have to be oriented downwards. And on this inner cylinder, if I want to point into the air, then I'm going to be pointing toward the z-axis. That might be a little bit hard to read in the picture, but notice that I don't want to point into the solid between the cylinders. I want to point into the air, and to go toward the air would be toward the z-axis. Kind of for a third example, I think you're getting this. If you had a solid sphere initially, but then you blew a bubble so that bubble was on the interior. So how do I indicate that? Do I do the whole thing with dashes? So you have a sphere with a bubble in it. Then this solid, the solid between those two spheres, has two surfaces. One surface is the outer sphere, and the other surface is the inner sphere. The outer sphere gets the unit normal, which points into the air. The inner sphere is going to be the unit normal that points back toward the center of that sphere. So again, pointing into that air pocket, not pointing into the solid between the spheres. So the divergence theorem is the fourth of what I've been calling the big four. And let me remind you what those were. First of all, we found we saw the fundamental theorem of line integrals. And the fundamental theorem of line integrals related an integral along a curve in space to the value of a function at its two endpoints. Next, we saw Green's theorem, where we had a region in the plane and its boundary curve. And Green's theorem related a certain integral over R to a related integral over the boundary curve. Then we saw Stokes' theorem, here we had a surface in space and its boundary curve. And Stokes' theorem related the integral over the surface in space to a related integral over its boundary curve. And then finally, with this lecture, we're seeing the divergence theorem, which relates the volume over a solid in space to a related integral over its boundary surface. So in each case, we're seeing an integral over some object related to the integral over the boundary of the object. Well, there's a language in math called differential forms. And it turns out that using the language of differential forms, all four of these integrals can be written in one way. They all say that the integral over a certain object R is the same as the integral over of something else over the boundary of R. So this little delta represents boundary. So we're relating the integral over some object to the integral over the boundary of that object. And this is where the differential forms come in. Omega is the differential form, and d omega is the derivative, known as the exterior derivative of the differential form. So it turns out that if you know the language of differential forms, all four of these theorems can be written in this very same way. And if you're curious, now that's getting toward the end of the semester, if you're looking for something to read over the break, I have actually two great references if you want to learn more about differential forms. One of them is the textbook by Ted Shiffrin, called Multivariable Mathematics. Which is a nice combination of Calculus 3 and linear algebra. And the other is by Hubbard and Hubbard. Called Vector Calculus, with a bunch of other words. Ted Shiffrin is actually who taught me most of what I learned as an undergraduate at University of Georgia. And his Multivariable Mathematics is a really well-written book, and it really, at least for me, carries the flavor of what he was like as a teacher. Another interesting thing is if you look on YouTube, again, his name is Ted Shiffrin, there's a set of videos which covers his entire course as he teaches through multivariable mathematics. So that'd be something interesting for you to check out perhaps over break. The book by Hubbard and Hubbard is kind of idiosyncratic. It also covers linear algebra and Calculus 3 in kind of an odd way, but it's one that really appeals to me. So this book is on my retirement reading list. I've kind of skimmed through it and liked what I saw. I'll probably go back through and end up reading it cover to cover eventually.